There's a robot right now, sending us a message from the edge of forever. It takes 7 hours for its whisper to reach us, traveling at the speed of light. It's further from home than any functioning machine we've ever built. And it just discovered something that breaks physics as we know it. The universe is glowing. And it's glowing twice as bright as it should be. By the end of this video, you'll understand exactly how a mission designed to photograph Pluto accidentally became our best shot at detecting dark matter, and why we only have a decade left to find the answer. January 19th, 2006. NASA launches the fastest spacecraft ever built toward a world we'd barely seen. Pluto, a frozen mystery at the solar system's edge, 9 years away. The plan was simple. Fly past Pluto at 32,000 miles per hour, snap some pictures, send them home, mission complete. And in July 2015, New Horizons delivered. Those images, the heart-shaped glacier, the blue atmospheric haze, mountains of water ice, they rewrote the textbook on planetary science. But here's what nobody expected. Instead of ending, the real mission was just beginning. Because 5 billion miles from Earth, in near absolute darkness, New Horizons started detecting light that shouldn't exist. Light that could rewrite our understanding of what the universe is made of. And the clock is ticking. Here's a question that sounds simple. How bright is the universe? Not just the stars you can see, not just the galaxies we've cataloged. The total light. Everything. You might think we'd know this by now. We've been doing astronomy for thousands of years. We have space telescopes, gravitational wave detectors. We've photographed galaxies from when the universe was a child. But we don't know. We can't know. Because there's a problem. Imagine trying to hear someone whispering across a football stadium while a rock concert plays. That's what measuring the cosmic background light is like from Earth. Our atmosphere scatters light. The sun drowns out everything. Even in space, zodiacal light, sunlight reflecting off dust in the solar system, creates a constant glow. It's like trying to see stars from inside a snow globe. The particles are in the way. For decades, astronomers tried to subtract this foreground light mathematically. They'd observe a patch of sky, identify every star and galaxy, subtract those, account for zodiacal light, and the answer kept changing. Too many assumptions. Too much uncertainty, until New Horizons got far enough away that the rules changed. At 5.5 billion miles from the Sun, beyond Pluto, deep in the Kuiper Belt, something remarkable happens. The zodiacal light drops to nearly zero. It's like leaving the city and driving into the deep desert. At first, you still see the glow of streetlights on the horizon, but eventually, you reach true darkness. New Horizons reached that darkness. The quietest place any human-made instrument has ever operated. And that's when Dr. Todd Lauer had an idea. Lauer is an expert in measuring faint light. He'd spent years studying the cosmic optical background, the technical term for how bright is empty space. In 2020, he realized New Horizons was in the perfect position, far from zodiacal light, far from planets, with a high-quality camera designed to image faint objects. So he proposed something audacious. Turn the spacecraft around, point it at the darkest patches of sky, and measure the darkness itself. NASA approved, and in December 2020, New Horizons became humanity's most distant light meter. The requirements were brutal. The spacecraft had to point away from the sun, all planets, the galactic plane where most stars concentrate, any bright stars, and any nearby celestial objects. They had to power down every single LED, every indicator light, even the instrument heaters temporarily. It's like being a photographer trying to capture the faintest aurora. You need the right night, clear skies, no moon, away from city lights, and your camera has to be perfect. Except this photographer is 5 billion miles away, and you can't just try again tomorrow. They got 7 usable images. 7 patches of sky, each carefully chosen, each a 2-year journey to observe. Then came the hard part. Each image contained thousands of objects, stars, galaxies, cosmic rays, detector noise. Lauer's team spent months identifying every single one. They used star catalogs, galaxy databases, spectroscopic data, Machine learning algorithms. One by one, they subtracted known sources. They modeled residual zodiacal light and removed it. They filtered cosmic ray hits. They accounted for stray light from the spacecraft itself. And when they finally removed everything they could account for, when they'd subtracted every known source of light in those images, there was still light. A lot of light. When the results were published in January 2021, the astronomy community went quiet. The cosmic optical background, the total light in the universe, was approximately twice as bright as all known galaxies could account for. Let me put that in perspective. Imagine you're an accountant. You add up all your clients' income sources, salary, investments, side business. Then you check their bank account and there's twice as much money as you calculated. Something's missing. Either you missed half their income sources, or money is appearing from somewhere you don't understand. That's where astronomy is right now. We have three theories. Each one would revolutionize our understanding of the cosmos. Maybe there are countless ultra-faint dwarf galaxies we've never detected, each one too dim to see individually, but collectively producing enormous amounts of light. Current models predict a certain number of low-mass galaxies formed in the early universe. But what if those models are wildly wrong? What if galaxy formation in the first billion years after the Big Bang was far more prolific than we thought? Here's why this matters. Galaxies form inside dark matter halos. If there are millions more small galaxies, it means dark matter clusters differently than our models predict. It would affect calculations of cosmic structure formation, dark energy measurements, the universe's expansion rate, and the ultimate fate of everything. But there's a problem with this theory. The James Webb Space Telescope has been searching for these ultra-faint galaxies, and while it's finding some, it's not finding enough to explain New Horizons measurements. Which brings us to the second theory, and this one's stranger. Picture two galaxies colliding. Not like cars crashing. Galaxies are mostly empty space, but the gravitational forces are catastrophic. Stars get ripped from their home galaxies. Entire stellar streams flung into intergalactic space at hundreds of kilometers per second. These intracluster stars, or orphan stars, belong to no galaxy. They're cosmic refugees wandering the void. And here's the extraordinary part. Studies of nearby galaxy clusters suggest that 10 to 50% of all stars might be these wanderers. Half of all stars. Not in galaxies, just drifting. If half of all stars are orphans, scattered in the space between galaxies, they'd be nearly impossible to detect individually. They're too spread out, too faint. But collectively, they'd produce exactly the kind of uniform, diffuse glow New Horizons detected. Think of it like looking at the Milky Way from Earth. You can't see individual stars in the dense parts. They blur into a continuous band of light. Same principle, but on a cosmic scale. If this theory is right, our entire mental model of the universe is wrong. We think of galaxies as islands in a dark ocean. But the reality would be more like foam, continuous, interconnected, no true emptiness. But there's a third theory. And if this one's correct, New Horizons didn't just find missing light. It found something we've been searching for since 1933. In 1933, astronomer Fritz Zwicky noticed something impossible. Galaxies in the Coma cluster were moving too fast. Based on the visible matter, they should fly apart. But they didn't. Something invisible was holding them together with gravity. He called it Dunkel Materie, dark matter. 90 years later, we know dark matter makes up 85% of all matter in the universe. We see its gravitational effects everywhere, in galaxy rotation, gravitational lensing, cosmic structure. But we've never detected a dark matter particle directly, ever. So here's the question that keeps physicists awake at night. What if dark matter isn't completely dark? Most particle types are unstable. Given enough time, they decay into lighter particles, releasing energy. What if dark matter particles, whatever they are, occasionally decay? Very rarely. Maybe one particle in a trillion decays per year. Each decay releases a tiny amount of light, undetectable from a single event. But multiply it across the entire observable universe. 10 to the 24th stars, 10 to the 80th atoms, and perhaps 10 to the 85th dark matter particles, each with a tiny probability of decay. The accumulated light from all those decays, over billions of light-years of space, could equal exactly what New Horizons measured. Imagine a stadium with 1 million people. Each person's phone screen is almost off, just barely glowing. Individually, you wouldn't notice, but fill the whole stadium, and from a distance, you'd see a definite glow. That's the dark matter decay hypothesis. Except the stadium is the universe, and the phones are fundamental particles we've never directly seen. If New Horizons detected dark matter decay, it would be the first time in history we've observed dark matter doing anything except gravitating. It would tell us dark matter is made of particles, not just curved space-time or modified gravity. It would tell us those particles can decay, meaning they have specific properties and lifetimes. It would tell us they interact with photons, even if extremely weakly, and we could estimate their mass based on the decay energy. This would guide every dark matter experiment on Earth. Detectors deep underground, particle accelerators, everything. We'd finally have a direction to search instead of stumbling in the dark. But here's the problem. Right now, we can't distinguish between these theories. The signal New Horizons detected is consistent with hidden galaxies, orphan stars, dark matter decay, or some combination of all three. To solve this, we need more data, observations from different angles, measurements at different wavelengths, longer integration times. We need New Horizons to keep measuring year after year, building up signal, reducing uncertainty. But there's a cruel irony. The spacecraft is dying. New Horizons doesn't run on solar panels. At 5 billion miles from the sun, solar panels would be useless. The sun from New Horizons looks like just another bright star. It provides 0.1% of the light it gives Earth. Instead, the spacecraft carries a plutonium-238 radioisotope thermoelectric generator, an RTG. Plutonium-238 naturally decays, producing heat. Thermocouples convert that heat directly into electricity. No moving parts, no fuel to burn, just physics. When New Horizons launched in 2006, the RTG produced 202 watts. That's about the power of 2 old incandescent light bulbs. Not much, but enough. Your laptop charger probably uses more power than what's running this entire spacecraft. Cameras, computers, transmitters, heaters, everything. Today, in 2024, the RTG produces approximately 173 watts, and it drops about 4 watts every year. Plutonium-238 has a half-life of 87.7 years. Sounds like a lot. But the thermocouples also degrade. The conversion efficiency drops. By 2035, New Horizons will be running on less than 140 watts. By 2040, maybe 120 watts. And at some point, maybe 2038, maybe 2042, nobody knows exactly. It won't be enough. Right now, every watt is accounted for. The transmitter needs 28 watts to send signals across 5 billion miles. Guidance and control takes 30 watts, keeping antennas pointed at Earth. Computers use 20 watts, 1990s-era rad-hardened processors running the show. Instruments are variable but hungry for power. And heaters are critical, as temperatures plunge to 300 degrees. When you want to do a cosmic optical background observation, you need the camera at 12 watts, extra processing power at 8 watts, and longer transmit times to send data home. Something else has to shut down, usually heaters. The team has to carefully calculate how long can we turn off heaters before instrument damage occurs. It's a gamble every single time, and the gambling gets harder every year. Dr. Alan Stern, principal investigator, calls it threading the needle. Once per year, sometimes less, conditions align for a cosmic background measurement. The spacecraft orientation has to be away from sun and galactic plane. There must be sufficient power available. Instruments need to be warmed up and functional. No higher priority science targets can interfere, and a communication window with Earth must be available. The window might last a few hours, maybe a day. They took measurements in December 2020, June 2021, and November 2023. Each measurement takes about 10 seconds of actual exposure time, but requires hours of preparation and pointing. The data then takes 7+ hours to reach Earth, crawling across space at light speed. And every year they wonder, will we get another chance? Right now, New Horizons is 5.5 billion miles from home. That's 58 astronomical units, 58 times the distance from Earth to the Sun. Light from the Sun takes 7 hours and 20 minutes to reach it. When mission controllers send a command, they wait 14 hours and 40 minutes for confirmation it worked. Nearly 15 hours for a round-trip conversation. Imagine texting a friend and waiting more than half a day for message read. That's every interaction with New Horizons. The spacecraft is currently the farthest functioning human-made object in the solar system. Voyager 1 is farther, but it's left the solar system entirely. It's in interstellar space now, a different domain. New Horizons is still technically in our sun's domain, but barely, at the edge, in the twilight. And every day it gets farther, lonelier, colder, but it keeps working, keeps measuring, keeps calling home across the void, because what it's discovering matters. So where does this leave us? We have 3 explanations for the ghost light. We can't yet prove which is correct, and our best tool for solving it is on borrowed time. The James Webb Space Telescope is actively searching for ultra-faint galaxies in its deep field observations. If it finds enough of them, millions more than current catalogs show, the hidden galaxy hypothesis wins. But so far the counts aren't there. JWST sees faint galaxies, yes, amazing ones, but not enough to explain New Horizons' excess light. Ground-based telescopes are mapping intracluster light in nearby galaxy clusters, trying to measure orphan star populations. Early results suggest orphan stars are common, maybe very common, but extrapolating from nearby clusters to the entire universe? That's uncertain. And for dark matter? There are proposals, just proposals, to send small, dedicated probes even farther than New Horizons, specifically designed to measure cosmic backgrounds. But those missions are decades away. Maybe they'll never launch. Right now, New Horizons is it, our only functioning observatory in the outer solar system's quiet zone. The team is planning observations for every remaining year, 2024, 2025, 2026, each year adding to the dataset, refining the measurement, reducing uncertainty. They're also trying creative solutions, selective heating, only warming critical components, data compression, sending more science with less transmission time, instrument rotation, cycling which tools stay active, reduced telemetry, fewer health reports, more science. Every watt saved is time bought. Every efficiency gain is another year. But eventually, the math becomes impossible. Current best estimates. New Horizons can operate until sometime between 2035 and 2040. It won't be sudden. The shutdown will be gradual, agonizing. First, simultaneous instrument operation becomes impossible. Pick one, camera or spectrometer, not both. Then, heaters fail permanently. Instruments freeze and die one by one. Communication becomes intermittent. The transmitter can't maintain constant contact. Finally, there won't be enough power to run the computer and maintain antenna pointing simultaneously. The last transmission will be simple telemetry, engineering data, battery voltage, temperature readings, and then silence. But New Horizons won't stop moving. Newton's laws don't care about batteries. It's traveling at 31,000 miles per hour relative to the sun. At that speed, it will pass the heliopause, the true edge of the solar system, sometime in the 2040s. It will reach the distance of Proxima Centauri in about 40,000 years. It might encounter another stellar system, maybe never, maybe millions of years from now. Long after human civilization has either spread to the stars or returned to dust, this machine will still be out there. It carries no golden record like the Voyagers, but it has a CD-ROM with names of mission team members and images of Earth. A message in a bottle, cast into an ocean so vast that our entire solar system is less than a single drop. Think about that. Something we built with our hands, something that bears our names, something launched when YouTube was brand new, drifting through the darkness until the stars themselves die, still chasing the dying light. So here's what we know. 5 billion miles from Earth, a robot designed for a 10-year mission is performing science nobody planned for. It measured the brightness of the universe and found light that breaks our models. That light is either revealing millions of hidden galaxies from the early universe, illuminating a cosmic web of orphan stars drifting between galaxies, or showing us dark matter decay for the first time in human history. We have maybe 10–15 years to figure out which one before the power dies and silence falls forever. That's why New Horizons' journey through dying light isn't just another space mission. It's potentially humanity's best shot at answering the most fundamental question in physics. What is the universe made of? We built a spacecraft to see Pluto, but we accidentally built something far more important. Our most distant eyes, staring into the cosmic darkness, measuring the light we cannot explain. And every year, those eyes stay open is a gift we should not waste. Sometimes the most profound discoveries happen at the edge of our reach, in the final moments before the light goes out.